Section 9.2, rigid objects in equilibrium. If a rigid body, something that's not wiggly, is in equilibrium, neither its linear motion nor its rotational motion changes. In other words, the acceleration in the x direction and the y direction must be equal to 0. We've seen this before. We applied that to Newton's second law, where the sum of the forces in the x and the y direction is normally equal to mass times acceleration, but if the acceleration is 0, then the sum of the forces must also be equal to 0, independently in the x and the y direction. Now we're going to add in another parameter, that in equilibrium, the angular acceleration is also equal to 0. And so the sum of the torques also must come to 0. That the rotation, in most cases, we'll look at static equilibrium where nothing's moving, but even in equilibrium where things are moving, they're all moving at constant velocities and speeds. So we don't have to worry about any acceleration or any change in velocity. So our formal definition, equilibrium of a rigid body is a rigid body is an equilibrium if it has 0 translational acceleration and 0 angular acceleration. In equilibrium, the sum of the externally applied forces is 0, the sum of the externally applied torques is 0. So anytime you hear equilibrium or just about things balancing, being at rest, that's a sign that these three equations will apply. So I recommend you plan to use these equations. Our basic definition of equilibrium is that all the accelerations are equal to 0. And that then connects to this by Newton's second law, that the sum of the forces, the sum of the torques must also be equal to 0. How do we use this in solving problems? Well, we have another reasoning strategy. So first we're going to select the object of interest, then draw a free body diagram that shows all the external forces acting on that object. So anything outside that object that's pushing or pulling on it. Choose a convenient set of x and y axes for each object and resolve all forces into components that lie along these axes. This is similar to what we did with forces in Newton's second law. Well, step 4, apply the equations that specify the balance of forces at equilibrium, so the net force in the x and the y directions equal to 0. Boom, pretty straightforward. Where this is slightly different is with torques, we're going to select a convenient axis of rotation. If things are in static equilibrium, that means they aren't necessarily rotating. So we don't have a fixed axis of rotation like we did with the door hinge. That means we can choose our axis of rotation, and there will be choices that make more sense than others. Once we've chosen that axis of rotation, then we can set the sum of the torques about that axis equal to 0. Finally, solve the equations for the desired unknown quantities. All right, let's try this out, see how it goes. So example 3, a diving board. A woman whose weight is 530 newtons is poised at the right end of a diving board with a length 3.9 meters. The board has a negligible weight and is supported by a fulcrum 1.4 meters away from the left end. Find the forces that the bolt and the fulcrum exert on the board. All right, so as we're looking at this, let's keep going back and forth to the reasoning strategy. So select the object that we're going to apply the equations to. Well, notice it's the forces the bolt and the fulcrum exert on the board. That to me suggests we want to look at the forces acting on the board. All right, pretty straightforward. Draw a free body diagram that shows all the external forces acting on the object. Okay, so first we're going to draw the forces on our diving board itself in the picture here. So the woman is exerting a force on the board. How is the woman exerting a force on the board? Well, the woman has a weight, right? That 530 newtons. So the woman's weight is going to be in what direction? Pushing down on the board, absolutely. To be consistent with the book's notation, I'm going to write this as a W, even though I typically try to avoid that notation. This is the 530 newtons. Great. What other forces do we have on the board? One that we often like to think of is the weight of the board itself, the force of gravity pulling on the board, in other words. But notice here it says the board has a negligible weight. That means our board is very light compared to the other forces interacting. So we're able to ignore that weight, which is a nice thing because we could account for it, and we'll see how to do that in the next section, but it's just one more thing to consider. So we don't need to worry about that here, but we will have forces from the bolt and the fulcrum. What direction will these forces be? Well, some can be suggested from the picture itself and the wording. The fulcrum is the balance point, and notice it's supporting the board. So I'm going to guess that that is an upward force. If the fulcrum has an upward force, then the bolt, in order to balance the forces, must be holding the other end of the board down. Otherwise, the woman's weight would just tip the entire board, right? You can try this out yourself. If you pull down on one end and you have two other forces, what way do you want them to go? So that works pretty well, right? Where I'm pushing down with the woman's weight, my fulcrum is supporting it in the middle here, and then on the end, I'm pushing down with the bolt to clamp that board there. So to label these, I'll just call it F1 and F2. You can call it F bolt and F fulcrum if you like. All right, so that's pretty good. Checking back. We want a free body diagram that shows these, and choose a convenient set of X and Y axes. Resolve the forces into components that lie along these axes. Apply the equations that specify the balance of forces at equilibrium. All right. So as we look at this, we notice that all the forces are acting in the vertical direction. That helps us out a lot. Then we can just say, hey, let's make X the horizontal direction as before, and Y the vertical direction. And indeed, that's what's been done here in this corner image. Now, if we want to sum the forces, which I recommend is a good step to do at this point, then we notice all the forces are in the Y direction. So we're only going to focus on the sum of the forces in the Y direction, and we're going to set that equal to 0. We can sum the forces in the X direction too, we just won't get anything interesting. And here, conveniently, the forces are all up or down, so we can just put our forces here and then put a negative sign for if they are going down. So F1 is in the negative direction, F2 is in the positive direction, and then the weight is in the negative direction. All right, so notice that was very quick to get an equation because there's no acceleration. It's pretty straightforward. We could say that F2, if we add F1 and the weight to the other side, F2 is equal to F1 plus the weight of the woman, 530 newtons. Now, in this case, we don't know F1 or F2, so this isn't enough to solve the problem. But we can get more information by solving another equation, and then we can use this to fill in any gaps. So this is a great start. I recommend you start by summing the forces because you get equations very quickly. Next up in our strategy is looking at the torque. Now that we've applied Newton's second law, the sum of the forces is equal to 0, we need to sum up the torques. And for summing up the torques, we choose a convenient axis of rotation. So how do we choose what is a convenient axis of rotation? Well, the key is that wherever you place the axis of rotation, if you place it on a force, that force is not going to contribute any torque, because that will be a distance with a lever arm of 0. So what we want to do for torques is place the axis of rotation at one of our unknown forces. You can choose. The unknown forces are the bolt or the fulcrum. Either of these work. Based upon the distances specified, it's slightly easiest to specify or put our axis of rotation at the bolt. And I encourage you to explicitly draw in this axis of rotation. Really helps. Now that we've done that, we can think about summing up our torques and what that means. Now, when we want to calculate torque, we know that the torque is the force times the lever arm. And we're going to be looking at the sum of the torques, so adding together a bunch of torques and setting that equal to 0. So that means for each force that has a torque, we're going to need to know its lever arm. So we can do a subscript for those. So for force 1, because we've placed the axis of rotation there, the lever arm is just 0. There's no distance from the axis of rotation to the force. Awesome. Then we could draw in a lever arm for force 2. So I could call that L2. And then also for the weight. And that's going to be L sub W. And now when we sum up the torques, we'll use those parameters. So I could write out my torques. I could even include torque 1, torque 2, and torque W. It's all equal to 0. This first one, as I mentioned, torque 1 is just 0 because the lever arm is 0. So we don't need to worry about that. What about the others? Well, for the others, we need to consider if they're causing a positive or a negative rotation in order to put in the signs here of plus or minus. So let's start with force 2. If force 2 is the only force acting on this diving board, the diving board about this axis of rotation would rotate upward in the counterclockwise rotation, right? That would be a positive torque. So we can fill in a positive sign here. Awesome. Versus notice the weight, if that was the only force acting on the diving board about this axis of rotation, that would cause the entire diving board to go in the counterclockwise, the clockwise direction, excuse me. Like a clock, CW, clockwise direction. So that would be negative. This tells us that torque 2 has to be equal to the torque of the weight. And we can fill in our lever arms and our forces and thus solve this. So let's take a look at the solutions written out here. So the sum of the torque, here's torque 2 minus torque of the weight. And if you solve for F2 by adding the weight's torque to the other side and dividing by L2, then you can find that force 2 is just 530 newtons times that full length, the full lever arm, the length of the diving board will be the lever arm for the weight, 3.9 meters, divided by L2, which is the lever arm from the axis to where the fulcrum is, 1.4 meters. So that comes out with F2 is 1,480 newtons. So we just found the force of the fulcrum. What about the force of the bolt? Well, at this point, we could either sum up the torques again with a different axis of rotation, or more simply, we can look at the sum of the forces. Right? Remember we saw that F1 is negative, F2 is positive, weight is negative. Well, now we know what F2 is, so we can solve for F1. And we'd find that F1 is equal to F2 minus the weight, which comes out to 950 newtons. So there's an example of seeing an equilibrium problem where we used the balance of the forces and the balance of the torques in order to solve a problem that previously we would not have been able to do. We'll see one more example in the next video.